11.1, Basic Identities in Trig Algebra. In this section, we're going to work with some identities we already know, and we're going to introduce some others and do a little algebra with them. So, for example, there are what we call reciprocal identities, and these we already know. These are cosecant is the reciprocal of the sine function, the secant is the reciprocal of cosine, and the cotangent is reciprocal of the tangent. And if we reciprocate these, then we get our original. So these are called the reciprocal identities. All right. Next, let's talk about the quotient identities. And again, these you should know. One of them is the tangent function, which is a quotient of the sine and the cosine. And then if we reciprocate this, we get the cotangent, which is the quotient of the cosine to the sine. Now the Pythagorean identities. For a right triangle with legs A, B, and hypotenuse C, we know that the Pythagorean theorem works. But now let's apply this right triangle. Let's put it on the unit circle. Okay, and if it is with a hypotenuse of 1, then this point right there has coordinates cosine of x and sine of x. And cosine of x, remember, is the x coordinates. That would really be the same thing as a. The sine function would really be the same thing as b, all right, the y coordinate. So applying it to the Pythagorean theorem, we get this, the cosine of x squared and plus the sine squared equals 1 squared, which is just 1. All right, and this is a Pythagorean identity. However, we write this a little bit differently. Instead of writing cosine of x in parentheses and squared, we put the two actually inside, and we write it like this. And we read this as cosine squared of x, sine squared of x, and 1. So cosine squared of x plus sine squared of x is equal to 1. And that is a Pythagorean identity, and we use this particular identity quite often. Okay, so this is one you really should memorize, or you will use it so often that you'll just know it. Okay, now what I'm going to do is I'm going to take this and I'm actually going to divide every term by cosine squared of x. All right, and when I do that, the first term, cosine squared over cosine squared, just becomes 1. The sine squared over cosine squared, sine over cosine is tangent, so that becomes tangent squared, and 1 over cosine is secant, that becomes secant squared. And so this becomes this Pythagorean identity. All right, let's do that same thing, but this time divide every term by the sine squared of x. All right, cosine over sine is cotangent, so the first term becomes a cotangent squared. Sine squared over sine squared is 1, and then 1 over sine squared is 1 over cosecant. Is a cosecant squared, and so we get this Pythagorean identity. So these are the Pythagorean identities. Now the negative identities. If we say for some angle x in the triangle here, this coordinate will have, this point will have coordinates cosine of x, sine of x. Now instead of taking a positive x, let's take an angle of negative x. Notice it ends up with the same x coordinate, all right? Well, actually this coordinate would now have coordinates, this point would now have coordinates cosine of negative x, sine of negative x. Okay, the x component, or the x term, and the y term. Okay, but notice if we're in this quadrants 1 and 4, the cosines are both positive. These are going to end up being the same. So this term, this point, is going to have the same x coordinate as this point. Okay, so really I can rewrite this as just cosine of x, and the y coordinate is going to be the same size, but in the opposite direction. So instead of taking positive value for the sine of x, we're going to take that same value, but now we're going to take it negative. So the coordinates now become this: cosine of x, the cosine of this, the coordinates of this point are cosine of x, and then negative sine of x. Okay, quadrant 4 has positive x coordinate, positive cosines, negative sines. Okay. All right. So. But that gives us some identities, because now we can say that the cosine of negative x is the same as the cosine of x. And we can say that the sine of negative x is the same as the negative of the sine of x. And these gives us two negative identities. Okay. Okay, and then we're going to use these to get the negative identities for the other 4 trig functions. For example, let's talk about the secant. The secant of negative x is 1 over the cosine of negative x. Okay, but the cosine of negative x is the same as the cosine of x. And 1 over the cosine of x is the secant. So this gives us that the secant of negative x is the same as the secant of x. And this really follows from the cosine function. Through a similar analysis, we can come up with the cosecant of negative x is the negative cosecant of x. And this follows because the cosecant is a reciprocal of the sine, and so the same relationship for the sine applies to the cosecant. All right. Okay, now let's talk about the tangent. The tangent of negative x is the sine of negative x over the cosine of negative x. The sine of negative x is the negative sine of x, and the cosine of negative x is the cosine of x. And so what this gives us is the negative of the tangent of x. And by the same reasoning, we can come up with the identity for the cotangent, and it ends up being the same, which makes sense if you think about it, I hope. So these are the negative identities. Okay? All right, now let's apply these to some examples. Example number 1. Let's simplify this expression. Okay? And we're really going to be using just these 2 negative identities. Okay? All right, in this case, we're going to be using these. Okay, well, the sine of negative x is the negative sine of x. The cosine of negative x is the cosine of x. And then this negative sine over cosine is just a negative tangent. And so this simplifies to the negative tangent of x. All right, what about this one? The tangent of x is going to be the sine over cosine. And the cosine of negative x is the same as the cosine of x. So this breaks down to this. Okay? And now I have a cosine of x in the numerator and a cosine of x in the denominator. And the cosines and sines, the same rules of algebra apply to these as they do to any other variable. So if one's in the numerator and the other's in the denominator, I can just cancel them out. And so this becomes sine of x. All right, what about this one? Cotangent is the cosine over the sine. Sine is just a sine, and secant is 1 over cosine. So I'm going to write it like this now. Okay. Now, I'm going to simplify this thing. Let's just look at the numerator. In the numerator, the same thing here is going to happen as in number 2. There I have a sign in the numerator of the numerator, and I have a sign in the denominator of the numerator. One's in the numerator, one's in the denominator. I can cancel them out. And then what I'm left with is, in the numerator, just cosine of x. Okay? So I have cosine of x over 1 over the cosine of x. Okay, now, it's a little weird, but if we have numerators in denominators and denominators in denominators, and this could really be cosine of x over 1, so I can have a numerator in the numerator and a denominator in the numerator. If you divide fractions, okay, what ends up happening is that this cosine of x in the denominator of the denominator comes back on top. Okay, you can prove that if you divide these fractions, because this bar really means divided by. Okay, all right, so cosine of x over 1, if we want to write that as a fraction, divided by 1 over the cosine of x, what's going to end up happening because of multiplying by the reciprocal, this cosine of x is going to come back on top. And that's going to become, then, the cosine squared of x. All right, this one. Now, remember, the tangent is a sine over cosine. So I'm going to write the numerator. Well, actually, I recognize this as one of my Pythagorean identities. 1 plus the tangent squared of x is equal to the secant squared of x. So I'm going to substitute in the secant squared of x for the numerator here. And this is what we're going to get. Okay? And then the secant is 1 over the cosine. The cosecant is 1 over the sine. So I can write it like this. Okay? All right. Now, cosine squared of x is in the denominator of the numerator. it goes down on the bottom. Sine squared of x is in the denominator of the denominator. It comes back on top. And so what we end up having is sine squared of x over cosine squared of x. All right? Again, you can prove this to yourself if you divide that fraction by that fraction. All right? And then sine over cosine is tangent, so that becomes tangent squared of x. And that's our answer. Now, if you did not remember this Pythagorean identity, and you just substituted in sine over cosine for tangents, okay, and then 1 over sine for the cosecant, you would end up getting this answer as well, okay, as long as you did all of your algebra correctly. So you don't need to necessarily use this identity. It would save you a little bit of work in the end, but if you didn't remember that and you substituted in sine over cosine for tangent, you would still come up with that answer, okay? As long as you did all the algebra correctly. All right, next. What about this one? Well, over time, you will recognize that 1 minus cosine squared of x really can be simplified using our Pythagorean identity, cosine squared plus sine squared equals 1. Because if I subtract cosine squared of x from each side, then what we get is the sine squared is equal to 1 minus cosine squared. And then I can substitute in the sine squared for 1 minus cosine squared. And I get this, okay? Now, notice I have sine squared of x over sine of x. So this is really a squared over a, all right? And if this is a squared over a, I can cancel out 1 from the top and bottom. Likewise, I can cancel out one of the signs from the numerator, and then the denominator will cancel out as well. And so I'm just left with sine of x. Remember, sines and cosines and tangents and cotangent and all that, they follow the same algebraic rules as any other variable. Okay? So we can cancel out top and bottom to just get sine of x here. Okay, now, what about this one? Well, as I mentioned, these follow any other rules of algebra. So if I just consider cosine of x is just x, you may recognize this trinomial x squared plus 2x plus 1 as a perfect square of x plus 1. Okay? And so we can essentially factor this into x plus 1 quantity squared. Okay? And so this numerator can be factored into cosine of x plus 1 quantity squared. Okay? Now, that's the numerator. Now the denominator, sine squared of x, by the same argument as we used in number 5, we can substitute 1 minus cosine squared of x in for sine squared of x. Okay? All right, now I recognize the numerator as a difference of perfect squares. 1 is a perfect square, cosine squared is a perfect square. And so this is really kind of a squared minus b squared, or 1 minus x squared. And remember our property of algebra, where if I take a difference of perfect squares, that'll be 1 minus x and times 1 plus x. Okay? And so now I can write this denominator as 1 minus cosine and 1 plus cosine. All right? A squared minus b squared is equal to a quantity a minus b times quantity a plus b. Remember that? Okay, we can apply that to here. All right, now notice addition is commutative, and what that means is I can flip the order. A plus b, same as b plus a. So the numerator, I'm going to switch around that order. And then finally, notice that I have 1 plus cosine of x in the denominator. I have 1 plus cosine of x quantity squared in the numerator. I can cancel one of those out. Okay? And then finally, our answer becomes this. And we can't get any farther than that. That's as far as we can simplify. No more cancellation can occur. So that's our answer. Okay, last one. Now, what I see here is one fraction minus another fraction. If I want to subtract fractions, I'm going to need common denominators. So I need a common denominator between these two. All right, now the foolproof way of getting common denominators is just to multiply the denominators together. All right, so I'm going to multiply the first one. I need a denominator of cosine of x times the quantity 1 minus sine of x. Okay, to get that over with the first term, I'm going to multiply top and bottom by cosine of x. And I'm going to multiply top and bottom of the second term by 1 minus sine of x. So cosine of x over cosine of x, remember special form of 1 times this first term. Special form of 1 minus sine of x over 1 minus sine of x times the second term. And then we'll have a denominator of cosine of x times the quantity 1 minus sine of x for each term. Okay? So I'm going to write it all over that same common denominator. And then in the numerator, the first term will be cosine of x times the cosine of x, which is cosine squared of x, minus the sine squared of x. I'm sorry, minus the sine of x times the quantity 1 minus sine of x. Okay. Okay. Now I'm going to distribute the sine of x through that parentheses, and we're going to get this. Okay. Note the minus sign. Negative sine of x times negative sine of x is positive sine squared of x. And now I recognize cosine squared of x plus sine squared of x. So I'm going to reorder it a little bit, okay? And then remember, cosine squared of x plus sine squared of x is equal to 1. And so that numerator becomes 1 minus sine of x. And then I have 1 minus sine of x in the numerator. I have 1 minus sine of x in the denominator. They cancel out. And lo and behold, I get 1 over the cosine of x, which is just the secant of x. That's kind of amazing that this complicated thing that we started with just breaks all the way down to just the secant of x, which is much simpler. Okay, one more thing that we can do, that we're going to do in this section, is to verify some identities. And we can do that by showing that the left-hand side and the right-hand side are the same. Now, it doesn't really matter which one you make the same. You can make the right one equal to the left. You can make the left one equal to the right. It doesn't matter, just so long as they end up being the same on both sides. Okay. This time, I'm going to work with the term on the left side. Now, notice I have two terms that are added over the same common denominator. Okay, well, I can separate those. I can write that as 1 over the cosine of x plus sine of x over the cosine of x. Okay, I can put each term over its common denominator. That's legal. Okay, and then notice 1 over cosine of x, that's secant. Sine of x over cosine of x is tangent. And so I get I get secant of x plus tangent of x on the left-hand side, secant of x plus tangent of x on the right-hand side, and so this identity is verified. All right, so by simplifying one side or the other, or converting, shall we say, we can make one side look like the other, and that means the identity is valid. Okay, so this is another identity. Not one we use very often, but nonetheless an identity. Okay, so you'll have some of these to do in the practice problems as well. All right, so go ahead and get started on that. You can use these examples to do the 11.1 practice problems.